The artificial intelligence landscape is structurally divided into two distinct methods: systems that classify data and systems that generate it. Discriminative AI is built for classification. These systems map inputs to a fixed set of target classes, sorting data into predetermined categories. Because these models are designed to find existing labels, they cannot produce anything that falls outside of their fixed target classes. This logic drives the most common enterprise applications today, including sentiment analysis, image classification, and optical character recognition. Generative AI uses a different approach. These systems model underlying data distributions to synthesize entirely novel outputs that resemble the patterns found in their training data. This synthesis is made possible through three primary architectures: generative adversarial networks, diffusion models, and autoregressive models. Moving from bounded classification to unbounded generation requires a significant change in training methodology and how computational resources are allocated. Understanding this architectural taxonomy is necessary to ensure that the chosen model is actually capable of the specific task at hand. For decades, enterprise AI was defined by the need to efficiently process inputs that arrived in fixed sizes. To meet this need, engineers relied on discriminative architectures like logistic regression, support vector machines, and gradient-boosted decision trees. These models are highly efficient because they create mathematical boundaries between known data types, allowing for high-speed classification. The challenge arises when these systems are forced to handle data that varies in length or complexity. Solutions like convolutional neural networks and long short-term memory units were developed to process these more complex, variable data streams. More recently, transformers have become the dominant component for scaling these discriminative models to handle massive datasets. But despite these advancements in scale, the underlying logic remains. These models are built to find boundaries, not to ideate new content. Generative adversarial networks, or GANs, were designed to overcome the limitations of those boundaries by using a dual network system. In this architecture, a generator creates data from random noise, while a separate discriminator compares that output against a reference of real data. These networks train together. The discriminator learns to identify fakes, while the generator trains to confuse it with increasingly realistic patterns. Ideally, the generator eventually becomes skilled enough to create content that is indistinguishable from the training data. However, GANs are notoriously difficult to train because they are prone to a failure state called model collapse. Model collapse happens when the generator stops creating varied data. Instead, it finds a single narrow output that tricks the discriminator and repeats it indefinitely. When this happens, the model stops being useful for generalized applications, as it can no longer produce diverse results. While GANs proved synthesis was possible, the instability of this adversarial process led to the development of more reliable alternatives. Diffusion models emerged as a successor to GANs, replacing adversarial competition with a stable, step-by-step training regime. The process begins by teaching the model to systematically degrade clean data with layers of visual static until the original structure is lost. The model then learns the specific mathematical steps required to reverse that damage, stripping away the noise to recover the data. Once the model has mastered this recovery, it can be given a starting input of pure, random noise. By applying its noise extraction techniques to that random static, it can ideate entirely new, high-fidelity images. This specific architecture is now the foundation for the most popular modern image generation services. By focusing on systematic noise recovery rather than adversarial competition, diffusion models provide a more stable path for visual generation. Autoregressive models are the oldest generative approach, with roots in statistical sequence modeling rather than traditional machine learning. These models generate sequences by calculating the probability of the next element based on all the elements that preceded it. After mapping this distribution, the model selects the next element to build the sequence. This selection process is tuned by a parameter called temperature. A low temperature makes the output more deterministic, while a higher temperature flattens the probability curve, allowing for more varied or creative results. Today, this statistical approach is powered by transformers and LSTMs to handle massive amounts of text. However, raw autoregressive models were originally limited because they could only complete a sequence without any regard for a user's actual intent. Statistical prediction alone is not enough for an enterprise tool. It requires an additional layer to guide its responses. To turn raw statistical predictors into functional assistants, models undergo an alignment stage. Alignment is a secondary training process that teaches the model to prefer specific input-output pairs over others. This relies on human feedback to evaluate the model's outputs, effectively reweighting the probability pathways to favor those that humans find useful. Reinforcement learning is the primary technical framework used to apply this feedback across billions of parameters. As a result, the model moves beyond simple sequence prediction and learns how to answer questions and follow complex commands. This alignment is the specific mechanism that enables a generative model to interface directly and safely with human users. Without this stage, these models would remain sophisticated statistical calculators rather than the interactive systems we use today. The most recent gains in AI have come from training massive generative models with over 100 billion parameters on more than 10 terabytes of data. This massive scale, combined with human feedback alignment, has significantly expanded the operational capabilities of large language models. These models now demonstrate a level of zero-shot accuracy that allows them to perform tasks they were never explicitly trained for. This generalized reasoning allows a single generative model to perform the same categorization tasks once reserved for narrow, discriminative classifiers. Because of their general knowledge, these LLMs can now execute sentiment analysis, entity recognition, and data classification as a byproduct of their core training. For enterprise architecture, this represents a major shift in how resources are deployed. For many specific tasks, the accuracy of aligned generative models is now sufficient to replace the dedicated, single-purpose discriminative classifiers that once dominated the field.